Now that we're done calibrating, we can start capturing. First, let's talk about the positioning and recording of a single rigid body. A single rigid body can refer to many objects. For example, drones and unmanned vehicles used in scientific research. These can be considered single rigid bodies. There are also VR applications, such as VR glasses and controllers, which can also be treated as single rigid bodies. In this video, we'll start with drones and unmanned vehicles used in scientific research. We'll use a single rigid body as an example to introduce how single rigid body capture works. First, as you can see on our screen, we have a drone. We need to attach a number of marker points to the drone. Regarding the number of marker points needed, we generally need at least 3 markers. With 3 markers, our system can establish a plane, allowing the drone to have rotational data. To enhance the stability of single rigid body capture, we usually add more marker points. We can attach 4, 5, or even 6 marker points to add redundancy to the single rigid body, to minimize the risk of losing points and data during motion. We need to arrange these marker points asymmetrically. If the marker points are symmetrically placed during capture, the software may mistakenly identify the direction as the opposite. This can lead to misidentification of the direction. Therefore, we recommend setting the marker points in an asymmetric layout. After we set up the marker points, we can place the object in our field. In our software, you can see the 4 marker points on the drone. Our coordinate system now has the z-axis pointing up. You can see the x-axis is facing this direction. The y-axis is facing this direction. To create a single rigid body, we first need to click on the freeze button at the bottom of the screen. That's the freeze button. Then we hold down the shift key, and we can box in a couple of marker points on the object. Then we click the right mouse button, choose Create Rigid Body. Then we type the name of the rigid body. For example, I type in fly. We click on Create, and we can see at the center of these selected marker points. It will then translate our geodetic coordinate system to define the base X, Y, and Z axes of the rigid body. This pink vertebra represents the axis of the rigid body towards the Y-axis. After we've created this, we'll click on Unfreeze at the bottom of the screen. Now let's move the single rigid body. We can see the single rigid body in the motion capture program. You can see that in the software, the single rigid body is also moving in real time. To get the data of the single rigid body, we usually have 2 ways. One is to get the data in live mode, to get the data in real time. To get the data in real time, we need to click on the data casting pane in the View menu. Then we need to set the NIC address. That's the address of the server that we're broadcasting to. I'm going to set the server address by default to the motion capture IP segment 10.11.198. Then we can start the SDK. At this time, our data is already in real time, broadcasting to the patch and broadcasting on the LAN. At this point, we can use our SDK, like C++, Python, or other SDKs, to get our data. I'm going to use our C++ SDK demo to get the data. You can see the data is now broadcasting in real time. This SDK demo, we can get the data for each marker. We can get the X, Y, Z coordinates of each marker point and their velocity, acceleration, frame timestamps, the name of the single rigid body of the object under test, fly and its corresponding rigid body, its X, Y, Z coordinates, and the QX, QY, QZ, and QW data. This is real-time acquisition. If we want to export the data, we will use the file at the bottom of the interface. Input the file name. For example, I'll enter test1, and then we click on the record button. Then we can move our subject around. We can click on the stop recording button and then the software will prompt us. It will ask about the data being saved and the file name. We click on OK. Then we can click on Pause Playback. Click on the Edit button on the bottom left. Then we click on the file on the right in the drop-down menu. Select the data we just collected, Test 1. Inside the view, we can click the Play button to play back the data. If we want to export the data, we can click on the file in the upper left corner of the interface. You can click on Export TRC file and Export XRS file. The TRC file contains the 3D coordinates of each marker point in the rigid object. We can open it and take a look. We can create an Excel file. We drag this test fly TRC file into it. You can see the first column is each frame. The second column is the time of each frame. The third column is the time sum, followed by the X, Y, and Z coordinates of marker 1, marker 2's 3D coordinates, marker 3, marker 4, and their 3D coordinate data. The XRS file contains single rigid bodies, frame number, time sum, and its XYZ coordinates and the QX, QZ, and QW data. That's the introduction of single rigid body capture.